Now for chapter 16 summary, which is normal distribution. Chapter 16 was the last one that we had a look at. Now, with normal distribution, it's all about these bell curves here. So we've seen a heap of these so far, and it's supposed to be a way to kind of represent how likely different events are. So events that are closer to the mean, we might see there's more space in there. The larger the space means the larger the probability. Now, something that we need to realize is that if we worked out the area underneath this bell curve here, it's always going to be 1. Now, probabilities of all outcomes, they always add to 1, don't they? So that makes sense that it adds to 1 underneath there. Now, we kind of had a bit of a look at the 68, 95, 99.7 rule. That shows us how much probability there is between different standard deviations. So we're told that one standard deviation from the mean, so our mean is right in the center here, it's represented by that there, which is mu. When you guys text through questions, you normally just use m, which is fine, but that letter there is mu, it's a Greek letter. This here would show one standard deviation above the mean, above mu, so that little standard deviation symbol there, that's actually sigma. But it doesn't really matter. You just need to know that means standard deviation. So this is showing one standard deviation above the mean, two standard deviations above the mean. That should be sigma, not pi. Three standard deviations above the mean, and the same down here. So that's 1 below, 2 below, and 3 below. Now I just want to look at each of these little sections that I've kind of spaced out here. And work out exactly how much probability is between each of those boundaries it has on either side, using this 68, 95, and 99.7. Alright, now, if it's symmetrical, which it absolutely is, and that's something you need to know and I'll talk about, that means with our 0.68 here, half of it's going to be there and half of it's going to be there. So this section here is going to have 0.34 in it, and this one here is going to have 0.34 in it as well. Now let's look at the 95 now, or the 0.95. Now 0.68 of it's already been taken, hasn't it? So if we take our 0.68 from 0.95 and then split that in half, because half of it has to go there and half of it has to go there, we're going to have 0.135 in there and 0.135 in there. Alright, now the next one. If we have 0.997 and 0.95 has already been taken up, so we'll take that 0.95 from the 0.997, divide it by 2, because half it goes there, half it goes there. Our probability in this section is 0.0235, and the same over here. Alright, and the last one, so 1 minus 0.997, divide that by 2, because half it needs to go there and half it needs to go there, means we've got 0.0015 in there and 0.0015 in there as well. All right, so that's where all the different probability is located. So if we look at this section here, we could say that 0.34 of the probability is located between the mean and one standard deviation above the mean. Let's look down here. 0.0235 is located between 2 standard deviations below the mean and 3 standard deviations below the mean. Now this works for any normal distribution. Doesn't matter what the mean is, doesn't matter what the standard deviation is. So I'm going to go down here to these two examples that I've drawn up. Now they're not all going to look exactly the same. Some are going to have large standard deviations. Now standard deviation is a measure of the spread. See how this large one's kind of flattened out? That's what's going to happen if your standard deviation is large, if it's spreading out a lot. If your standard deviation is small, that means it's going to be squished together. Okay, so it's going to end up being tall and thin. What we need to recognize is, though, the area underneath this one and the area underneath this one is exactly the same. It's always 1 because the probabilities always add to 1. Okay, now let's look back up here for a second. Now these might have different means and different standard deviations. It does not matter, because even though this one looks different, sort of, you've got 0.34 in there, you've got 0.34 in there, you've got 0.135 in there, and so on. They're all the same. Okay. Now I've written down here always symmetrical. So hopefully we can see that. It's pretty much a mirror image of each other if you draw that line up from the mean. Okay, now we need to use that for a lot of questions. Now, if it's symmetrical, I'm just going to kind of color some stuff in to hopefully help you out a little bit. This here, as we kind of saw before, has the exact same probability of that one here. We could even say these two here, so that one and that one, we have the exact same probability of falling between here and here as well. Okay, so getting a result from here onwards is equal to getting a result from there onwards. Getting a result between here and here is equally as likely as getting a result between here and here. Okay, now that works for these ones as well, as we showed. All right, now getting a result between here and here would mean the same for down here. Would mean that bit there, or that bit there, because it's symmetrical, they're the same. Okay, so they are all comparable. All right, now there's basically a couple of main types of questions that you're going to come across in normal distribution. They're going to involve either of these two things here. Okay, so you're either going to be given an x value and ask for a probability, and to solve that you'd have to use normal CDF, or you're going to be given a probability and ask for an x value, so the opposite. If you're asked to do that, you're using inverse normal. All right, so we're going to practice with a couple of those ones now, but what I want, what I'm going to really emphasize is, you see when we type it into our CAS, it asks us for area. It means the area below that x value. Okay, I'm going to show you very soon. Now, before I get into these couple of questions, some people might wonder, how do we know that it's a normal distribution? Well, it's going to tell you every single time. So if we look at this one, it says the weight of lolly bags are normally distributed. That's how you know. It's going to tell you every single time. Okay. Right, now let's try to answer it. So the weight of lolly bags are normally distributed with a mean of 200 grams and a standard deviation of 5 grams. Find the probability of a result or an outcome which is greater than 207. So that must mean grams. Now, people send me their work and I look through it, and sometimes I see people drawing pictures and most of the time I don't. Now, the people that are drawing the pictures are the people that know what they're doing. So if I'm going to give you a tip, is draw the situation every single time. If you can see what's going on, it's going to make your life so much easier. Now, some people like to draw things differently, but I'm going to show you how I like to do it. I think it's the best way. I think it will work for you. If it doesn't and you prefer some other way and that works, that's fine. But if you're struggling, do this. All right, so let's show what we know. Normally distributed, so we've got a bell curve like that. Mean's always in the middle. It's told us that the mean is 200 grams, which is just there. Now, I'm going to show what the mean is again over here, and I'm also going to show what the standard deviation is, which is 5 grams. Now, I'm going to keep reminding you this, but I've told you standard deviation here. Sometimes they'll give you variance. You need to change it to standard deviation. If you make a mistake and don't change it, it's going to stuff everything up. So be very, very careful with that. Now, it's asking us to find the probability that the result is greater than 207. Now, 200's here, 207 must be a bit further up. We're trying to find this here, this shaded bit. I want that. Okay. Now, 207, if the standard deviation is 5, 207 means it's a little bit above one standard deviation above the mean. Now, I've been given an x value, this is the x value, and I want to find the probability. So if I'm given an x value and I want to find the probability, I'm using normal CDF. Norm CDF. Now I'm going to go to my CAS and show you how
We're
to do
looking
it.
for normal CDF, so we'll go menu, probability is our topic. We're after a normal distribution, so we'll go to distributions. We can see we've got normal PDF and normal CDF. CDF is cumulative. Now we were after 207 and above, so that's not just a single reading, that's a span, so we're going to go to normal CDF. Now our lower bound, we wanted above 207, didn't we? So our lower bound is going to be 207, and there's no real cap on the top, is there? So it can go up to infinity. You can just write infinity in, and it'll work. Now it's asking for the mean of the distribution. We were told that was 200, and the standard deviation we were told was 5. It did not work. It's because I didn't spell it right. Okay, there we go. So we've just worked out that the probability of a result greater than 207 is 0.0808.
So B, if the probability of randomly selecting a lolly bag less than X grams is 0.75, find the value of X. Now I'll repeat again, draw it. You need to draw this. Okay, so that's what I'm going to do to show you. Here's our distribution. Our mean we know was 200. Our standard deviation was 5. Right, and it said that if the probability of randomly selecting a lolly bag less than X grams is 0.75. Right, so we need to shade 0.75, which is below X. So X will probably be about here. And we've got this whole part here shaded. And that comes to 0.75. Okay, now let's think back to before. We've been given a probability and we're asked to find a value for X. That means we're using inverse normal. So let's go back to our calculation.
Same as before, menu, probability, distributions, but now we're after inverse normal because we've been given that probability, but we want the X value. It's going to ask you for the area, as you can see there. It's asking for the area below that X value that you're after. So you saw before that we shaded 0.75 below. So our area below is 0.75. Our mean is 200. Our standard deviation is 5. So it's told us that the X value is 203.3744. 3724, sorry.
So the answer's been written down here. That would mean that we've got 0.75 of the probability below this X value. So this X value here is 203.3724. Okay, let's move on to the next one. Now the next one is very similar. C is very similar to B, except there's one thing that people make a mistake on, and I need to make sure you're not one of those people. If the probability of randomly selecting a lolly bag more than Y grams is 0.61, find the value of Y. Draw it. Let's draw it again. So here's our distribution. Our mean was 200. Our standard deviation is 5. Now it's told us that the chance of selecting more than Y is 0.61. So 0.61, something like that. We've got 0.61 in there, that's the shaded bit, and Y would be here. We want to find out what Y is. Now, we're going to do the same sort of thing with our CAS, so it's going to be inverse normal because we're trying to find one of the values down here. Now this one up here, we were already given the probability of below that X value. This time here, we've been given the probability of above that Y value. We don't want the probability above, we want the probability below. We're after this bit. So if this is 0.61 and this whole thing adds to 1, that means this over here must be 0.39. That's what we need to enter because the CAS is actually asking, it doesn't specifically say it, but it's asking for the probability below that value that you're after. Okay, so don't enter 0.61, you'll be wrong. it's going to give you, that'll end up giving you the value over here. We're entering 0.39. The mean is still 200, the standard deviation is still 5. If you put that into your calculator, you'll get 198.6034. Alright, so that's 198.6034. Now looking at standard normal distribution. Now it's not really too much new compared to what we were just practicing. The standard normal distribution is just a specific normal distribution. So it is the one that has a mean of 0 and a standard deviation of 1, and it looks like this, the same as the other ones that we've just been doing. The only difference that you might see is normally we've got an x here on this x-axis. This time we have a z, and we've got this formula for z here as well. Now, try not to get confused with z. Z, as I've written down here, it just tells us how many standard deviations from the mean we are. So z is 1 just means 1 standard deviation above the mean. Z is 2 means 2 standard deviations above the mean. Z is -3 means 3 standard deviations below the mean. Okay, it's mainly used for comparison as well. Right. All right. So let's see how it can be used for comparison. All right. So Joe has just completed tests for 2 subjects. Now you might have seen questions like this before, where results were normally distributed. The mean and standard deviation for history was 70% and 6%, respectively. Joe scored 80%. The mean and standard deviation for biology was 78% and 4%, respectively. Joe scored 83%. Which test was Joe comparatively more successful in? Okay, so basically what we're trying to do here is see which one he has more standard deviations above the mean, or just which one has the highest Z value. Okay, so let's look at history first. Okay, now I will use this formula, but I'm just going to draw it first just so we can see, because it's always a good idea to draw it. Here we go. Alright, so this is history. We were told that the mean was 70 and the standard deviation was 6. Oops. And what did Joe get? He got 80. So Joe's got here. Alright, cool. Basically we want to see how far above the mean he is here. So we can do that using this formula. Alright, so Z equals, now we put our x value in first, so our x value is 80 minus the mean, which we were told was 70, and we're dividing it by the standard deviation, which is 6. Okay, so our Z is 10 divided by 6, so 5 on 3. Cool. So that's just telling us that Joe's result is 5 on 3 above the mean. Standard deviation's above the mean. Okay, so that's how he's went on history. Let's see how he's gone for biology. Alright, so again, let's draw our curve. Now we were told that the mean was 78 and the standard deviation was 4. 78, and Joe has got an 83, so he's above the mean again. Okay, now let's work out what the Z score is. So we need our X value, which is 83, take away our mean, which is 78, divided by our standard deviation, which is 4. Okay, so the Z is going to be 5 on 4. Okay, so we can see that the Z score for history is higher means he's more standard deviations above the mean compared to this one. Okay, so that would mean that if we're going to compare how well he went for both of them, he's done a better job in history, even though he got 80% compared to in biology where he got 83%. Okay, so that's how we use Z-score to kind of make a bit of a comparison. We've just used the Z-score formula, which is kind of bringing us over into finding the mean and standard deviation. This sort of question is something that people have been having trouble with as well, so hopefully this helps you out a little bit. Let's read through the question first. In the examination, 30% of candidates fail and 10% achieve distinction. Last year, the pass mark out of 200 was 84, and the minimum mark required for a distinction was 154. Assuming that the marks were normally distributed, find the mean and standard deviation of the marks. Okay, so it's told us it's normally distributed here. Let's set ourselves up a bell curve. Let's draw it. Okay. Now, it hasn't told us the mean. That's something that we have to find out. So I'm going to put this line down the middle, but I don't know what's going there. I'm just going to leave it. All right, but it's told us 30% of the candidates fail. Okay, so I'm going to shade 30%. Let's just say it's around about here. That's 0.3. And that pass mark was 84. All right, so it's people that got above 84 passed, people that got below failed, and 30% of people got below. Next one we're looking at is the distinction. So the top 10% of people got distinction. So I'm going to shade the top 10% here. And also we're being told that the minimum mark required for distinction was 154. So that must be 154. Okay, so I've got a bit of info here. Hopefully we can use that. Now, I want to find our mean and our standard deviation. This is where our Z is going to come in handy. Okay, now what I'm going to do is draw another distribution below, but instead of being the X, this is the X one, I'm going to make this one the Z. I'll try to make it line up. Crap curve. Alright, now with our standard normal distribution, we know what our mean and standard deviation are, 0 and 1. And this is going to be our Z-score down the bottom. But these, because all normal distributions are the same, we can kind of transfer these probabilities across. So that bit there is 0.3. This bit here is 0.1. I reckon I'm going to be able to find the Z's that go here and here. Okay, now I've been told a probability of here. I want to find that spot. I also know what the mean and the standard deviation are of this distribution as well. So to find out this one here, I'm doing an inverse normal, aren't I? So inv norm. The first thing it asks me is the area under that value. So the area under that value is 0.3. Then it asks for the mean, and it asks for the standard deviation. And when I work this out, it's going to give me the number that goes there. For over here, it's the same sort of thing, isn't it? So we want inverse normal because we're after this reading. We know the probability. Now it asks for the probability below here. I'm not going to enter 0.1 because that's going to find me somewhere down here. Below here is 0.9. And the mean is 0 and the standard deviation is 1. Okay, so let's put those into our CAS and see what they are. When you do that, you're going to end up getting... No, that's the wrong one. Sorry. That was 0.5244. And this one was 1. 2816. Cool, so we've just found both of these things. So this one here is 0.5244. This one here is 1.2816. Now what that's saying is that we're minus half a one standard deviation. God, I can't even say it. We're half a standard deviation below the mean, and over here we're 1.2, almost 1.3 standard deviations above the mean. Now, because these things are the same, you've got a z-score of that corresponds to this x-score. You've got a z-score of this that corresponds to that x-score. Now, we're trying to find standard deviation and the mean. There's a formula which we used just before that we need to use to find this. So the z-score formula is x minus mean over standard deviation. See how we have that, we have that. We want to find those two. So let's start subbing some stuff in. Let's worry about this one to start with. So the z-score is that. The x-score that goes with that z-score is 84. The mean, we don't know what it is, so let's leave it like that. Standard deviation, we don't know what it is either, so let's leave it like that. Okay, so that's all we can do with that one. But we also have this one to deal with. All right, so here's the z-score. Here's our x-score. And these two we're trying to find out. Now we've got two equations. We've got this one with our mean and standard deviation, this one with our mean and standard deviation. We can use simultaneous equations to find out what they are. Now you can put this straight into your calculator, solve system of equations, and you're going to be able to get what your mean and your standard deviation are. Once you put it in, your calculator is going to say that your mean is 104.3258, 6, and our standard deviation is 38.7597. So we have them both, and we did that through comparing this normal distribution with a mean and standard deviation that we didn't know, comparing that to the standard normal distribution. The reason we went to the standard normal is for that one we know what the mean and standard deviation are, so it helps us out a little bit. Okay, so I'd absolutely suggest that you go through this process a couple of times because I see these questions pop up a little bit. So I mentioned earlier how important symmetry is, but also comparison between different normal distributions. Here are a couple of examples that take a bit of a look at that. So X has a normal distribution with a mean of 14 and a standard deviation of 2. Great. If the random variable Z has the standard normal distribution, okay, so we're talking about Z as well. So the standard normal distribution we need to know has a mean of 0 and standard deviation of 1. Then the probability that X is greater than 17 is equal to. And we have all these answers here that they seem to be in terms of Z. So we're going to have to compare the distribution that it talked about at the start to the standard normal, which is Z. So again, make sure you're drawing these things. I'm going to draw this distribution. Okay, so my mean's 14 and my standard deviation is 2. Now it's asked me down here, then the probability that X is greater than 17 is equal to. Let's just say 17's here. And it said it wants a probability greater than 17. So this is the probability that we're after. Okay. Now all these answers are in terms of Z, as we kind of touched on before. Now with this distribution, the mean's 14 and the standard deviation is 2. So 17 would have to be 1.5 standard deviations above the mean, wouldn't it? So if that was going to get a Z score, it would be 1.5 because it's 1.5 standard deviations above the mean. Okay, now this is what we're after. So we could probably say that the probability that we're after is that z is greater than 1.5. Let's go over here and see if that is there. I'm looking through, it says less than 1.5 there. It doesn't actually have it. This is where multiple choice questions can be a little bit tricky, and also where symmetry is involved as well. Okay. Now, as you know, as we've said however many times, this is symmetrical. So this probability over here, which is 1.5 standard deviations above the mean, it's going to be the same as 1.5 standard deviations below the mean. Okay, so these two probabilities are equal. If that's 1.5 above the mean, this is 1.5 below the mean. Okay, so this is the same thing. Now that one there would be the probability that z is less than negative 1.5. Now if we look through here, we've got it right there, don't we? Okay, so you see how sometimes it can be a little bit tricky and we need to think about symmetry and comparison between standard normal as well. There's some really important skills. So we've got our answer D for that one. We have another symmetry problem because it's important that we get the hang of this. It's going to be very similar to the last one. The random variable x has a normal distribution with mean 12 and standard deviation 7.5. If the random variable z has the standard normal distribution, then the probability that x is greater than 13.5 is equal to. Hopefully you can see that these two questions have been pretty much exactly the same. They've just changed some of the numbers. Right, so let's draw it. Remember, draw it every single time. So let's show our distribution. Means 12. And our standard deviation is 0.75. Okay, now again, all these answers are in terms of z, so we're going to have to compare it to the standard normal. Alright, it wants the probability that x is greater than 13.5. 13.5 must be somewhere up here, we can guess. This is the probability that we're after. Okay, now let's have a look at 13.5 and work out how many standard deviations away from the mean we are, because that's going to give us our z score or z value. Now if a standard deviation is 0.75, that would mean one standard deviation above would be 12.75, two standard deviations above would be 13.5. So our z score there is 2. So we could say the probability that z is greater than 2 is what we're after. Now again, let's look over here. Is that there? No, it isn't. It has less than 2, but that's not what we're after. This is where symmetry is going to have to be involved as well. Okay, so we've got this probability over here. We can find or show an equal amount of probability over on the other side. And because this is symmetrical, doesn't look perfectly symmetrical because of my slightly dodgy drawing, it should probably be further over here. Anyway, those areas are supposed to be equal. So if that's 2 standard deviations above the mean, this one over here must be 2 standard deviations below the mean. So that would be negative 2. If you wanted an x value, that'd be 10.5 because you're taking away 0.75 twice, but you don't actually need that. We're only really after the z. So we could also say the probability that we're after is when z is less than negative 2. Let's see if that's in the answers. Yeah, it is. It's A. The last thing we looked at when we were looking at normal distribution was a normal approximation to binomial. I think some people got a little bit confused because, you know, you've been doing certain things when we've been doing problems involving binomial and then other things with normal distribution. But what's important to remember is with binomial distribution, you can find a mean and standard deviation as well. So this is what the rules were, and I skipped over this part earlier, but with a binomial distribution, the mean, or they could say expected value, is your n value times your p value, so your number of trials times by the probability of success on each one. So that's important. We're going to need that. And our standard deviation is n times p times 1 minus p. Remember, 1 minus p is the chance of failure, and then the square root of all of that. So we might need that as well. So hopefully we can see that, with our mean and our standard deviation, we can kind of see a few similarities between binomial and normal. A few people were worried about how would they recognize whether they need to use normal approximation. It's always going to tell you. Okay, so let's read through this question and see what happens out of that. So a random sample of 2,000 people in a particular town, 2,000 is a pretty big sample, were asked if they were in favour of a new shopping complex. It's known that 20% of the people in the town are in favour of the complex. Okay, so that would be our n value, the 2,000 there, and 20%, or 0.2, would be our probability of success, so our p-value, using the normal approximation to the binomial distribution. See, it's told us the approximate probability that between 380 and 550 people in the sample were in favour of the complex is closest to, and there's our options. Right, so we're using normal approximation. All right, so we're gonna use a normal distribution. We just need our mean and our standard deviation first. Okay, so let's work out the mean of this binomial. So n was 2,000, p was 0.2, so our mean's 400. Great. Now we need our standard deviation. NP ended up being 400. 1 minus p is 0.8. So that means we're going to have square root of 320. Cool. We have our mean and we have our standard deviation. This is no different now. All we need to do is use our normal distribution. So I'm going to draw it as I do every single time so I don't get confused. There's my mean, 400. I've got these listed there already. I want to work out the probability that we have between 380 and 550. 380 is going to be somewhere here. 550 is going to be somewhere up here. Don't need to know exactly. So this is the probability that I'm after. Now hopefully we remember from the examples before, we're given these x values here. We want to work out a probability. So we'd have to use normal CDF. We're going straight to our CAS. So norm CDF. Go through the menus and find that. The first thing it asks you for is the lower boundary, which is 380. Then the upper boundary, which is 550. Then it wants the mean, which is 400. We work that out. And it wants the standard deviation, which is root 320. Now when you put root 320 into your CAS, when you go through the menu, make sure you put brackets here. Otherwise it's going to say it's missing brackets and it won't work. So you might have to put those ones in there. And once you've done that, hit enter, and it's going to tell you that your answer is 0.8682. And there it is, C. Okay, now before I finish up, I want to repeat, you need, when you're working with normal distribution, you need the standard deviation, which is sigma. Sometimes you might be given the variance. You don't want the variance, you want the standard deviation. So to get from the variance to the standard deviation, you need to square root it. Okay, so I'm going to write this down here. It's important that you remember because I don't want you making any silly, easy mistakes in our SAC or in your exams at the end of the year. So standard deviation is the square root of variance. That's important. If you have any questions, make sure you're talking to your teachers. There's not too much time before our SAC. Hopefully this has helped you out. Thank you guys.